All right, hello everybody. Welcome back to the learning modules for Texas Financial Derivatives. Again, my name is Matt Moskul, and today we're going to be talking about continuous probability. In the last video, we talked about discrete probability and the models and distributions that were associated with it, like binomial and Poisson. But today we're going to be talking about continuous, and the main difference between discrete and continuous distributions is that, like I said in the last video, discrete models can only take on a finite set of values. They're typically countable. However, with a continuous distribution, it can take on an infinite number of values. And a way to think about this is, for example, for a discrete distribution, you could think of rolls of a dice. It can be 1, 2, 3, 4, 5, or 6. And so we can count those, and we know exactly what they are. But for a continuous distribution, you could think of the speed of a car. It can be 80 miles per hour, it can be 60 miles per hour, it can be 65.2 miles per hour, it can be 30.123456735 miles per hour, and it can keep going on forever. There's an infinite number of values there's an infinite number of values in the middle of that the speed of your car could possibly be going. And with continuous distributions, there's a certain range of values that we can have, but in between those, anything is up for grabs. So let's talk about our first example of continuity, and that is going to be continuous uniform. Now, I think an easy way to think about a continuous uniform distribution is a function. Okay, I said in the last video, probability models are simply functions with their primary explanatory variable being the random variable x. The continuous uniform, it's a probability function as well, but it is constant, and with it being constant, it gives equal weight to every value that it can hold. So let me go ahead and write this down. So continuous uniform is a probability function of the form f of x equals c, where c is a constant real number. So we're going to do an example of showing this and showing how to think about continuous uniformity and how you compute probabilities within it. So let's do an example of this. So suppose you have a probability function. Let's say that's not how you spell probability. Probability function f of x equals 1/2 for x going from 0 to 2. And again, like we did with discrete models and distributions, continuous distributions must also follow the law of total probability, and I'll show you how this one does. And if you don't remember, the law of total probability simply states that the individual probabilities of all possible events in your model must sum to 1. And we're going to show how this works as well. But let's go ahead and draw this, okay? So here's our x-axis, here's our y-axis, and here's 1/2. Here's 0, and let's let this be 1 and this be 2. So this is the only place that our model exists. What if we wanted to know the probability x was between 1/2 and let's do 1. Well, I think you can best think of this as, suppose you have a brownie cake and you're blindfolded and you're gonna cut into it. You're gonna cut out a slice of it, a rectangular slice. Again, you're blindfolded, so you don't know what you're cutting in. You don't entirely know where you're gonna cut. And the idea of being blindfolded is that you're cutting in randomly. If I cut out a slice, what is the probability that that slice is in between the 1/2 and one foot or 1 inch mark, I guess, depending on how big of a brownie cake you want, however much you might eat. But what's the probability you'd be between the 1/2 and 1 mark out of a 2 foot long brownie cake? Well, like the law of total probability, the total area, this total area sums to 1. And you can just use the formula for area of a rectangle. Area of a rectangle is length times width. Our length here is 2. Our width is 1/2. 2 times 1/2 is equal to 1. And so, it satisfies the law of total probability. This area is all the possible occurrences or observations you could possibly have. So the probability that we're going to be in between 1/2 and 1 is simply that part of that portion of the brownie cake. So it's going to be here to here. So we're really only concerned with this part. We're only concerned with what's going on in this portion right here. So how might we do that? Well, the probability that you cut out that portion would be equal to that portion's area divided by the total area. So that would be area of portion divided by the total area. Well, the total area we have shown is just 1. What is the portion of this area, or what is the area of this little part? Well, it's the length, which is 1 minus 1/2, times the width, which is 1/2. This becomes 1/2 times 1/2, so it's 1/4, or 25%. This means that we have a 25% chance of cutting a slice randomly in between the 1/2 and 1 mark. A simple probability model for continuous uniform, it can be seen as this: the probability you are between numbers A and B of your continuous uniform distribution is simply going to be equal to B minus A minus your total length, minus your total amount of length. So I'll call this capital B and minus A. And I can show you how this is true. So we can do 1 minus 1/2 divided by 2 minus 0, because x goes from 2 to 0. This becomes 1/2 divided by 2 equals 1/4. So really the width doesn't matter at all. You can think about it as just being, here's a line, it starts at capital A, ends at capital B. This is little a, this is little b. The probability we're in this portion is just this part divided by the total length. That's what that formula means. So I would write that down. Look at this for a couple more seconds. I'm gonna get a drink, and then we'll jump on to how to generalize a general function and general definition of what a continuous probability model is. Okay. I'll leave this definition up just for a little bit longer. So not all of our probability functions will be constant. In continuous uniform, that is the case, but we want a more general idea of how to estimate and get the probability that our probability function takes on some value. In the last video, we talked about discrete probability functions, but in here, when we talk about continuous ones, there's another name for them. They're called a probability density function. So a probability density function is simply a function of a random variable x whose values are continuous within some range and satisfies the law of total probability. And how we show this is and satisfies the integral over all the x values it can take on of our function f of x with respect to x is equal to 1. And I'll say law of total probability. Now, I showed in the last example in continuous uniform, the area underneath our function must sum to 1. In this case, we had a height of 1/2 and a length of 2. 1/2 times 2 is 1. So the total area is simply 1. We might have a function that looks like this. It goes like this, and it's between two x points. We'll call it A and B or whatever. In order for this to be a proper probability density function, all this area underneath the curve must sum to 1. Well, how do we get the area? If y'all have taken any previous calculus classes, the area underneath the curve can be computed by the integral of the function, and this must sum to 1 to satisfy our law of total probability. This is why this must hold. And there's a name for the integral up to a certain point, and this is called the cumulative probability function the cumulative density function. And when we say cumulative, it literally means the word itself. You are accumulating all the values up, all the area up to a certain point. And so we're gonna show this. Actually, let me get rid of this thing so I have some room. But then I'll draw it again. So cumulative density function. The cumulative density function is simply a function that outputs the total area up to a certain value of our random variable x. And so let me erase the and is equal to, and is defined by f of x equals the integral of our probability density function, and this is big F of x. It goes up to x, and then it starts at the minimum point. So I'll just call this, for now, I'll just call this negative infinity. But generally, it's more so just the value you can take on. Like in the last example, it was from 0 to 2, and here it would be 0 to our value of x. And this is what this function means. So this says it is good. So to visualize this, we have a function that was like, and it went from here to here, and we'll call this, let's call this A, and call this X. The f of x that goes from A to X of this curve, which is our f of x, it would output all this area. This is what we mean by cumulative. It accumulates all that area up to a certain point. So, but what if we wanted to know the probability we were within 2 points? What if I want to know the probability that I was between here, we'll call it A, and then here we'll call it B. So, well, I could take this, if I wanted to get the probability between these 2 points, if I get f of b would be equal to all of this. So I still have this part left over. So if I want to get the area that's just between here, let me subtract this leftover part. What is this leftover part right here? Well, it's just f of a. That's the total area accumulated up to point A. So this will give us the probability that x is between A and B. This little point right here. So let's do an example of this. Actually, I'll erase. No, I'll leave that up because we kind of have it up there anyway. So, let's suppose we have a probability density function f of x that is equal to 2x, and it goes from, I believe it's for x going from 0 to, I believe it's 1, yes. Yeah, if I remember my example correctly. Okay, yeah, that should work. So let's graph it first. Here is 0, here is 1, and then we're going to draw 2x. Well, 2x is just a linear line, so we plug in 1 here, we're going to get 2 times 1 is 2. So we're going to have a point up here, and then we're just going to connect these two. This is our curve, you can think of it as. What if we want to know the probability that x is between 1/3 and 1/2? We want to know this. We want to know this part. Well, let's use our definition. The probability that x is between 1/3 and 1/2 is equal to f of 1/2, our CDF, minus f at 1/3. Well, f at 1/2 is equal to the integral of this. So that'd be 0 to 1/2, 0 to 1/2 of 2x dx minus 0 to 1/3 2x dx. Well, the integral of 2x is simply x squared. Minus 0 to 1/3 of x squared. The zeros will do nothing, so this just becomes 1/2 squared, which is 1/4, minus 1/3 squared, which is 1/9, which equals 9 minus 4, which is 5, over 36. So it's going to be a little bit less than 1/6. In order, you can also show this a little bit better. If you wanted to figure out the probability that x is between these points, you could simply do a to b of f of x dx, and it gives you the exact same thing. This says I'm only going to take the integral from here to here, from a to b of my probability density function, and it's just going to give you this area underneath the curve. But in this case, it's a straight line, but it's the same line of thinking. This is probability density functions and cumulative density functions. But now we're going to show one last thing, and it is the expected value of a probability density function. So, like we showed in discrete probability, the expected value in discrete probability, so I'll say discrete, was equal to the sum over all of our observations times the probability that they occur. It has a very close formula to the continuous case. For the continuous case, it's the same thing in a way. It is the value itself, our x, times the probability x occurs, which would be our probability density function integrated up to that point over all x. This is expected value in the continuous case, and it's very close. So let's do the exact same. Let's find our expected value with our example. So by our formula, the expected value would be equal to the integral over all x. We can go from 0 to 1, and x times our PDF, which is 2x with respect to x. This becomes 0 to 1, x times 2x is 2x squared. The antiderivative of 2x squared, based off the power rule, is 2x is 2/3 to the x cubed, because you add 1, so 2 plus 1 is 3, then you divide by it, so that's why we have 3, and then we divide it by 3. Plugging in our endpoints, we get 2/3 times 1 cubed minus 2/3 times 0 cubed, and we simply get 2/3 for our expected value. And so that means our average value in this case is going to be about 0.67 out of the entire 0 to 1. And you could actually figure this out if you took each and every single value and the heights associated with it and then just divided them all by each other, and you would get about 2/3. So now that we've talked about a general case of probability of the probability density function, the next thing we're going to talk about is the normal distribution, the Gaussian bell curve that you've probably heard of many, many times. Before that, I'm going to get a drink of water and then we're going to move on. I'll leave this up on the board. All right, so I'm going to try to wrap this up. So finally, we're going to talk about the Gaussian bell curve, which is this guy right here that you've probably seen many, many times. What this Gaussian bell curve, and it was constructed by Gauss himself. It is used in so many areas, but the main idea of it is that extreme values are unlikely. And you can see this too. You see the area underneath the curve, it is big. The area here, there's a lot of it, but as you move further out, there's less area on the extreme points as you get further away from our mean, our expected value. Our expected value is in the middle. It's our average of the entire thing, but as you get further out, the values get more unlikely. And the area underneath the curve follows the empirical rule, which says there's 68% of the area in this portion. There's, I believe it's 95% in this portion, and then 99.7% in this portion. So you see, as you move further out, the additional area is decreasing. For here, it's between the expected value and the first standard deviation is going to be 34 because it's 60 divided by 2. You move a little bit further out, I believe it's like, what is it? It's like, I think it's like 12 or 13% or something. And as you move further out, it gets down to like the 2% range, and it keeps doing this. It gets smaller, smaller, smaller. And it comes up so much in our life. There's shoe sizes, income disparity, IQ scores, you name it. And think about it. If the average shoe size for males, I'd say, is around like a 9 or a 10, maybe. I'd say you got probably like a 10. You don't often run into people with size like 15 in shoes, and you don't often run into people like, I'd say, adult males with size 4 in shoes. And because these are so unlikely, and same for IQs, you don't run into people that are the smartest of the smart of the pack, but you also don't run into people that are, the bottom of the barrel and can't really even form a sentence. Most people tend to be around the average, but deviating a little bit from it, and that's what makes up a lot of our professions. Is a lot of people are around the average in most respects, but they tend to excel in that one area. And it applies for income as well. The PDF for this normal distribution is equal to, so the probability x is between 2 points A and B in this portion shows between here and here. That is equal to the integral, which is what we've been doing, integral, and then this mess. 1 divided by the square root of 2 pi e to the negative x minus the mean squared divided by 2 times the standard deviation squared. dx. This is a mess, and we don't expect you to compute it by hand. In fact, I don't believe I've ever had to compute it by hand myself. These values are already made for you in the z-score table. And the z-score table says, based off how far your value deviates from the center, from its expected value, the z-score table will output the area up to that point. So you can think about the z-score table as giving us our CDF, our cumulative area, our cumulative probability. And your z-score is equal to your observation, your x, minus your mean, which is, we know it as mu, but it's your expected value, divided by standard deviation. This says the expected, let's say this is your x. X minus your expected value would then be this portion, with this little difference here. If we divide that by our standard deviation, it standardizes it. And so this is what our formula will be. And then then the probability that x is between 2 points will be the z-score table value, our cumulative value, which we denote by this, of z sub b, now z sub x, minus z sub a. We just showed this in the last example. It was our CDF f of b minus f of a, which gave you, if these are your 2 points you're worried about, it would give you this portion in the middle. So let's do an example of this. And I have it right here. Suppose your expected value, also denoted as your mu, is 2. And suppose your standard deviation, the average amount your values deviate from the mean, let's say that is, actually here, let's say this is 4 and this is 2. Based off this, what is the probability that x is between 3 and 8? Well, let's go by this. Is the CDF of your z-score of b of your 8. So 8 minus the mean divided by 2 minus the CDF of 3 minus the mean divided by the standard deviation, which is 2. This gives us 8 minus 4 is 4. 4 divided by 2 is 2. Minus 3 minus 4 is negative 1. Negative 1 divided by 2 is negative 1/2. So this would be, here's the second standard deviation, and then here's like the negative 1/2 standard deviation. And so we would get about all this point, with this being our center. We would get about all this area. And if you look up the z-score table, these values, which give you the left-hand side of the probability, would be 0.977 approximately minus 0.308, which is equal to about 0.668. So a little bit over 2/3. But anyway, this wraps up the video. We talked about what continuous distributions are, what continuous uniform distributions are. We then gave a general definition while applying the law of total probability and expected value to general PDF probability density functions, and talked about the cumulative distribution function, or the cumulative density function. Then lastly, we talked about the normal distribution, which is the Gaussian bell curve, which is in so many areas of your life, and its main idea is that extreme values are unlikely. Most people tend to be around the average of what you would expect. But this comes up in so many areas like IQ, shoe size, income, the stock market too, which we will see in this class, or which we will see in this club. And yeah, I hope y'all learned something. Please remember to follow the Instagram. It's at texas.fd. And if you have any questions, please feel free to like, comment, subscribe. If you have any questions, me and Austin will try to get back to you. to be also more one-on-one help. But that's all I have for the video. In the following lectures, we're going to be talking about binomial trees, eventually some Monte Carlo, and some Black-Scholes, and that's going to be very interesting, and it's going to show you how all these ideas tie together. So thank you guys.